This video covers the oceans of our Earth and starts us down the road on talking about the surface of the Earth processes and building on top of what we've said already about the interior of the Earth. The Earth is 70% oceans. These are deep, they're dark, a lot of it is not particularly well understood, and difficult to access. But they are a repository for materials from the continents and regions of intense crustal growth and destruction. There's a lot going on within and below the ocean surfaces. We'll just touch on them here today. I'm a fan of Randall Munroe's XKCD comic. You've seen several of these if you've seen other lectures by me. Randall does a really nice job of incorporating science and humor, and has done so once again in this diagram, which is perhaps better seen on its own. The link below, number 1040, should get you there. And he's showing the oceans here in two different modes. So he has what we call an exaggerated scale cross-section. That's most of the figure, to emphasize the changes in topography that we see on the ocean floor in a more presentable view where you can actually see some of the contrast. Embedded into this are two one-to-one cross-sections, the Marianas Trench and Mauna Kea, Hawaii, to give you a better sense of the actual scale of vertical to horizontal. There's a lot of interesting information on these and some humor as well. So check it out if you want to look at more details. But mostly I have this slide up to talk about the fact that we can see some features on the ocean floor, and that includes the deepest areas of the ocean. That is the Marianas Trench, which is the deepest point on the surface of our planet, down there at nearly 11 kilometers below sea level. And interestingly enough, the highest point on our planet is roughly 10 kilometers above sea level. That is, of course, Mount Everest. A nice little symmetry, complete coincidence, but a nice little symmetry to our planet. Roughly 10 above and 10 below sea level on the current ocean levels. And we'll talk a little bit about sea level, and sea level has fluctuated greatly over time. So we shouldn't get too enamored with the idea that there's some kind of symmetry to be preserved here. Most of the ocean floors are what we call abyssal plain, and that's most of the graphic that you can see there. But we have areas that rise towards the top. Mid-Atlantic ridges, we talked about those before, are shown in the middle of the diagram right here to illustrate where we have spreading centers. And we also have the continental shelves, areas where we have the oceans covering continental materials. We'll talk more about those in a minute. Accessing the ocean and the rocks underneath is a difficult challenge. The United States has a research vessel, the Joint Resolution, that is tasked with understanding what's happening on the ocean floors. So research scientists work in cooperation with a permanent drill crew in order to take this drilling vessel out to send drill them through the ocean water down to the ocean floor and extract information about the material underneath. The vessel itself is a floating laboratory and rock processing and sediment processing facility. They get data on site. They also take the materials and ship these to various labs after the voyage for a more detailed or different analyses. They get a pretty good look on board, and they get an even better look after the fact. That's how we know a little bit about our oceanic crust and its contrast with the continental crust. Specifically, we know, and we've talked about this before, that the abyssal plain is underlain by oceanic crust, a thinner piece, if you will, of the crust, comprised of basalts and gabbros, largely. And then under that is lithospheric mantle. the depth of which varies strongly under the oceans. Here in this graphic, it's shown at a fairly thick package until we see the contrast rheologically with the asthenosphere underneath. Remember that the asthenosphere is the part of the mantle that flows over geologic time. The lithosphere has to move by breaking. So, lithospheric mantle underneath the ocean grows vanishingly thin under the spreading centers, but here is shown as a thickened package, much thicker underneath the continents. And what this graphic is trying to illustrate is the transition from the abyssal plain to the continental shelf. Our current oceans are now incurring on top of the continents, so the edges of the continents are underwater, if you will. And again, we have a name for this. We call it a passive margin. We've seen this graphic before, or a similar one to it. What we're showing here is the oceans. The continents are grayed out and featureless. That, of course, is not the case, but the emphasis is on the ocean here. The red zones are the youngest rocks. From 0 and intense red to 9.7 million years ago. So, youngest rocks, of course, on the spreading centers. We're focused on the Atlantic Ocean here. Oldest rocks off towards the edges, where continental breakup first formed in the Jurassic over 154 million years ago. So again, if you want to go to the oldest parts of the ocean crust currently on the planet, you need to go offshore on the east coast of North America or in regions of the Gulf of Mexico. These are preserving Jurassic materials on the ocean floor. Everything else is younger than that as you approach the spreading center, which is the mid-oceanic ridge. We've talked extensively about that previously in this class, so hopefully this is familiar territory for you. The other thing we need to emphasize once again is that 154 million years is not that old. 4% of Earth history. So the ocean floors are very young. Again, we've just resurfaced our ocean floors. And again, the idea of a passive margin, an area where we transition from continental crust into oceanic crust. With current sea levels, we now have a significant flooding on the oceanic of the continental shelves, and that means these are vibrant areas for which life to accumulate, particularly biota that likes to grow hard parts, skeletal materials, out of the dissolved calcium carbonate that is in the water, the salts that we took away from the weathering processes on the continents. If you look offshore off of Long Island, New York, or New Jersey, you'll see that there's a wide plain that extends out into the ocean body, and then a steep drop-off known as the continental rise that takes us down into the abyssal plain, which is in the foreground of this picture. That steep transition is not featureless, and there are some topographic features, notably the outflow of the Hudson River system to the Hudson Shelf Valley and Hudson Canyon can be seen here as well. Some important features sort of synthesized in this diagram that we need to talk about is, again, the continental shelf. And this area that is wetted by the modern ocean surfaces. This is known as the neritic zone, and the neritic zone is the shore adjacent area that is just rife for life forms. Of course, the tides come in and tides come out, so there is a zone, somewhat exaggerated here, where we have wetting of the ocean surface on a daily basis, known as the intertidal zone. Once you get off the continental shelf and head down the continental rise, things get deeper faster. For one thing, when you get to about 1,000 meters or a kilometer below the surface, you've lost the ability to have any sunlight interactions. And it's pretty dark at the bottom, to be honest. The closer you are to the top, the more prolific photosynthesizing organisms will be. And that's the underpinning of the food pyramid, if you will, for the life forms living in the ocean. So a lot of life living in the photic zone, it gets scarcer, but not absent as you go deeper into the ocean. Other sources of energy are required if you're not going to use sunlight, and most notably areas in the deep ocean that see hydrothermal activity, particularly around spreading centers, are areas that too are rife with life because they take advantage of the energies being imparted from the interior of the Earth to underpin the food systems of those ecosystems. But there is a big change that happens. I've got it drawn here at about 4,000 meters or 4 kilometers, but it varies depending on where you are on the planet because it is controlled by ocean temperatures. This is the carbonate compensation depth, or CCD, above which you can have stable calcium carbonate, that is, limestone building materials, calcite forming materials, aragonite forming materials. Those are stable up here, so if you want skeletal hard parts that are made of that, you got to live above the CCD. And if you die and your materials fall below this, they will start to dissolve. Below the CCD, we of course can't have carbonate organisms. We can't have things like clams or snails or corals. They just can't live down here. They also are all heavily dependent on photosynthesizing systems, but even if there were a way to modify themselves through evolution to persist on the shores of these hot thermal vents, they couldn't have the skeletal materials they have. So the CCD tells you where those materials will be absent. The benthic zone actually extends along any of the interface with the crustal materials with the hydrosphere or the ocean. And the oceanic zone is this deep water zone. There are numerous life forms that are able to persist as free-floating organisms, but those that are benthic in nature, in other words, want to exist on a substrate, they dominate the neritic zone, and it's fair to say that they are more abundant in the neritic zone as well. So anywhere you see the cyan color in here is fair game for continental shelf. And where you are at the warmest parts of the planet towards the center of the planet on this Mercator projection, are places where you can have not only stable calcium carbonate within 4 kilometers of the surface, but also where you're likely to have prolific life forms, because warm water means more life. The direct sunlight doesn't hurt either. It's not just fossils you find in this area, it's accumulations of materials that have developed as a consequence of the interactions of the ocean water, outflow from the continents as well. And this actually creates a number of vibrant life systems that often build upon themselves in structures known as reefs. So a simplistic model might put this at the edge of the continental shelf, where organisms are thriving in the neritic zone and building up skeletal structures that persist over long periods of time. Currently, the corals are doing a good job on this on our planet, but if we dial back the time machine, we see that at other times sponges dominated this. Sometimes oysters were pretty good at this stuff as well. And some of the earliest reef-forming materials, which have persisted through time, are those of algal mats, that is, small unicellular organisms that depend heavily on photosynthesis. We can see this in Texas's higher point, Guadalupe Peak. This is actually an old reef system in an inland sea that has been preserved, largely dominated by sponges, but there's lots of other life forms here as well. I want to talk a little bit about tides, and I think the easiest way to introduce this is with this nice film that actually looks like it's geared pretty well for a pre-college audience. So simplistic in nature, that's good. Simplistic understanding helps us well to understand the nature of tides. I'm not going to play it in this video, but the link will be provided in D2L. So watch this separately when you get to this point, perhaps, or at some point thereafter. And then also pursue the rest of this video as well. So moving on, after learning a little bit about tides, the simplistic story is, of course, that it's the moon's fault. and the moon is causing this bulge around the planet. The bulge also happens to the solid part of the Earth, too. That's a little more complicated. And the sun's gravity is a factor as well. The combination of both lunar and solar forces can cause extremely high and low tides as a consequence of the joint pull of both gravitational systems. We'll leave it at the simple story here. Gravity is a powerful force that we explore in physical science, and it's in full operation. The moon has mass, the Earth has mass, the oceans have mass. They are attracted to each other as Newton stated they were. There are places where you can see stronger impacts of tides because it is amplified by the shape of the seafloor underneath. One such place is just northeast of the United States in Laurentian, Canada. The Bay of Fundy is a place where tides are dramatic on a daily basis, and this is because of the amplification of the ocean floor coupling with the tidal systems. So you don't need even a particularly strong tide to do things like this, which is leave boats high and dry for part of the day as a consequence of the tide going out. Tides have been operating on our planet since the inception of the oceans, so they are a factor in geologic history as well. They are a twice daily thing that happens. So regular seas going in and out produces the intertidal zone we talked about earlier. Of course, we live on a dynamic planet. The current ocean geometries are a consequence of the lithospheric plates. Some of the lithospheric plates are entirely oceanic in nature. Certainly the Pacific plate is an example of that. Most, though, are a consequence of both oceanic crust and continental crust being tied together and moving along on the lithosphere. North American plate is an example of that. The South American plate, of course. These are areas where we find continental crust adjoined to half of the Atlantic, if you will, that makes up the lithospheric plates that move around. That means that we can see some of the dynamicism that we talked about earlier in tectonics. One of the ways we get magmatism and volcanic expressions at the surface is by heating from underneath. These hot plumes of solid magma rise towards the surface and as a consequence start melting the mantle underneath. You have to have mantle melting to have magmatism. That is certainly the case in island hotspots like Hawaii, where the current activity concentrated under the big island, if you will, of Hawaii is a consequence of its position over the rising plume and generation of magma fairly deep in the upper mantle as a consequence of it, near the base of the lithospheric mantle. This propagates in magmatism and plutonism that is currently forming the island of Hawaii. But as we go back through the state of Hawaii and off into the islands that persist further out, these are just older expressions that have ceased to erupt, ceased to experience magmatism, because the plate has moved past where the hot spot is. So again, your older islands were formed further back in geologic time. They have gone cold and extinct as a consequence of moving off the hotspot because the lithospheric plate is moving past the hotspot, which is deeper in the mantle. There is a consequence to this, which is that erosion takes over, but erosion will only really get you to sea level as a consequence of where you're at. So moving in this direction in time, our active island becomes cold and becomes a source for reefal environments. The mountains that are generated from volcanism and plutonism are eroded away over time. The reefs persist over time and can leave a ring known as an atoll. With further cooling of the lithosphere, the entire thing can sink and become a submerged seamount underneath the water. Curiously enough, it was Darwin who first observed this and documented it on his travels worldwide, noting that this kind of life cycle for oceanic islands was quite common. Darwin, of course, was unaware of plate tectonics because that would come along much later. We can see this in the Hawaiian chain, of course. So if you pay attention to not only the state of Hawaii, but the seamounts and guyouts that extend outward and resurface here at Midway Island and go all the way out here until we join the Emperor chain. This is a continuation of that magmatism over the hotspot and tracks the Pacific Plate movement. So Pacific Plate motion has moved us past the hotspot in this direction for the past 40 million years. Prior to that, the Pacific Plate was moving in this north direction, and we could see that in the Emperor Seamounts. So that hotspot that's underneath Hawaii is a very long-lived feature indeed, stretching back to the Jurassic, to the oldest crust that we have present in this. And of course, what's happening currently is we're subducting the Pacific Plate underneath the Kurill and Aleutian trenches. The fate of the Emperor and Hawaiian chains is eventually subduction. Oh, one more thing before I leave that slide entirely. Hawaii is our U.S. state, and it is also a famous sort of poster child of this process. But a lot of these tracks you're seeing on the ocean floor out here, they're all consequences of this hotspot evolution of islands and seamounts over time. So with ocean rifting, we have the movement of the plates as they separate together. Some of this is quite slow, like the Mid-Atlantic Ridge, moving at 1.7 centimeters per year, often talked about in terms of how fast your hair or fingernails grow. That same kind of speed adds up over geologic time. And what we see under here, of course, is the generation of magmas in the underlying mantle because of heating from below. And again, I quibble it's not melting until you get closer to the lithospheric boundary, which is getting close to the surface at this point. What you get here, of course, is a mountain range underwater, the mid-oceanic ridge itself, with a valley running through it. So it is a rift system. As this heats up, there, of course, is abundant magmatism at the spreading center, but when it cools down, the entire system sinks, and that makes the oceans much deeper as a consequence once you move off the oceanic ridge. So as we move over time, we see sort of a flattening out to an equilibrium system at about 5 or 6 kilometers depth. That is our abyssal plain. And that is because the whole system is thickening and sinking further down into the gooier part of the mantle. Remember, it's solid, but it moves like a copper wire, the asthenosphere. This boundary here is that brittle ductile transition between the lithosphere and the mantle. Eventually, the fate of oceanic lithosphere is to be subducted back down into the mantle itself. Where we have the subduction zone, we have a trench, which is an eager recipient for sedimentary material, one that we talked about when we talked about sedimentary rocks. And of course, we have this downgoing slab that is releasing water and producing magmas to form a magmatic arc above this. This particular diagram shows the convergent boundary with continents, but of course we can have convergence where oceanic lithosphere meets oceanic lithosphere as well. These are vibrant areas on active margins. We don't have an extensive continental shelf here. So the opportunity to accumulate large populations of life that then are preserved over time are next to nil here. We're going to see lots of active burial and metamorphism to those materials over time. If you look at a cross-section of the ocean and think about some of the life forms here, not to scale. The types of life forms on our modern ocean are highly dependent, again, on the presence of light in the photic zone. So where we see our most active areas are in these areas where we have exposure to light. The aphotic zone is populated as well, but not as densely as the photic zone. And certainly these basal life forms, if you will, the phytoplankton and the zooplankton, these are the food sources for much of the life forms on our planet, including those in marine systems. So we see corals taking advantage of them, for example. And of course, these more primitive organisms end up feeding more complex organisms, and the whole food system is sort of based on that. But the deep sea also has life forms as well. And again, because we're below the carbonate condensation depth, we can't have aragonite or calcite organisms with those kind of structures. There are sort of areas in here where we have sort of faint light called the twilight zone of the ocean. But the deepest ocean, below 4 kilometers, sees no light whatsoever from the surface. We talked previously about the fact that the middle of a Mercator projection is the warmest part of our planet, and that certainly is the case. We see this recorded in seawater temps. So this is a heat map, if you will, again, a Mercator projection, showing where the warmest parts of our planet are, the orange zones on this, and unsurprisingly, they're right here near the equator, falling off in either direction as we move to higher latitudes. Appreciably colder near the poles, principally along the coastline of Antarctica, and of course the North Pole itself. And of course, this is a consequence of our exposure to direct sunlight. The planet itself has an axial tilt of 23.5 degrees, which, as it makes its circuit around the sun, one revolution on an annual basis, permits it to be exposed to direct sunlight from 23.5 degrees south, or the Tropic of Capricorn, to 23.5 degrees north, the Tropic of Cancer. Likewise, this variable exposure to sunlight also limits sunlight within what we call the Arctic and Antarctic circles. Parts of those areas are dark during their respective winter times, which exacerbates the cooling temperatures that we see in those parts of the ocean waters. But the ocean is not a stagnant system. It is coupled with the atmosphere, which we'll need to talk about in a subsequent lecture. And that means that heat is distributed and moved around in the atmosphere in these Hadley cell style motions where hot air is moving up into the troposphere, cooling off, and then returning at about 30 degrees south and 30 degrees north. This drives wind systems that couple with the oceans in terms of common waveform and storm systems. But also the ocean bodies themselves are moving as well, distributing heat, moving the hotter oceanic water to colder regions and colder oceanic waters to hotter regions. So the currents, which are independent of the winds, I shouldn't say they're independent of the winds. They're partially coupled with the winds, but strongly driven by the thermal systems of the water itself. So surface currents look something like this on our planet, and you can see that they're complex and somewhat in circular patterns, both on the northern and southern hemisphere. We can also see some principal currents that are important, such as the Gulf Stream current, which originates on the coastline of North America and finds its way all the way across the Atlantic to the shores of the United Kingdom and Ireland. This is why, despite its high latitude, areas like Great Britain are appreciably warmer than you would anticipate, given the rather cold conditions of northern Quebec at the same latitude. It's because the oceans are delivering warm water to that area. In the same way, warm water delivery is happening in a back and flow here at the middle latitudes between Asia and Australia and the Americas. The surface currents are important, but really this is a three-dimensional system with appreciable depth. And that gets a little bit harder to talk about, but the entire system is known as the thermohaline circulation system, and it is contingent on the shape of the modern oceans, and the conditions of the planet's temperature. But as it's currently working, this conveyor belt of heat, if you will, takes hot water, say via the Gulf Stream along the surface, and ends up cooling it by distributing it to the higher latitudes in the far northern Atlantic and North Sea. These return back down to the floor of the Atlantic Ocean to exchange with the water that is on movement. You can't have holes in the ocean, so any water that you move on the surface has to be replaced by water at depth that will eventually warm and return to the surface. Actually, this cold water persists quite a ways and distributes itself throughout the Atlantic system to pool at some of the deepest areas within the southern latitudes. So you can follow this conveyor belt around to find where the warming happens and returns warm water to the surface of the Earth. And although the red and blue sort of indicate hot and cold, there's a variety of temperatures that are being represented by those colors. And it's not merely the temperature that drives this system. There are changes in the concentration of salt ions that help with this as well, and of course change the salinity of the oceans themselves as a consequence of that. We can see that the oceans are higher in saline components, salt components, in about the 30 degree north and 30 degree south latitudes in the Atlantic, and less so in the Pacific. Also, the sort of stranded seas that make up the Mediterranean, the Red Sea, the Gulf of Aden, these are areas of higher salinity as well. Lower salinity areas exist in places where we're seeing less contribution from the continents. So if we look at this vertical movement that's happening to distribute water to the deep ocean floors, we see this along Greenland and Iceland, where cold, dense Arctic water is falling, if you will, because it's a gravitational system to the bottom of the ocean. We also see the incursion of cold Atlantic water displacing this at depth as well. The surface is much warmer, and this is generally known as a thermocline. Arctic ice is important to this system because Arctic ice is ice that forms on seawater. So this is apart from the kind of ice that we see on the continents, like Greenland, northern Canada, northern Siberia. This is just the ice that forms on the water. What's key to this is two things: not only how much surface coverage we have, but also how thick it is. And one thing that happens with the accumulation of ice on the surface is we're not allowed to freeze a lot of the salts that are dissolved in the ocean. So they accumulate in the non-freezing water that is left below these. That's an important system for the distribution of heat and currents within our ocean systems today. One thing that is alarming is that if we go back in time, we can find that the extent of ice cover on the northern polar cap and thicknesses were much greater than they have been recently. So this is data from the NSIDC, keeping track of what we're seeing in terms of accumulation and thicknesses at our poles. And we can see from this summer 2013 ice cap that the extent is lesser and the thickness is much lesser. That is a consequence, of course, of global warming. This may have consequences on driving this system. What we get with the formation of an ice cap is saline waters that are, of course, cold, and these sink to the bottom of the Atlantic. That system may not persist if we have no formation of ice on the surface, because saline water is much denser than the lower salinity water above it. So this helps drive the cooling system that sends water to the deep ocean. There are constant changes that happen across our planet, and one of the huge drivers of climate in the Americas, is the onset of this oscillatory system that happens every 4 to 10 years, known as ENSO, or the El Nino Southern Oscillation. ENSO is a big driver of how much precipitation the Americas will see in a given year. and we just recently came out of an El Nino system. What happens in El Nino is that we have an accumulation of hot waters, if you will, on the eastern side of the Pacific that migrate their way over towards South America uh, and heat the waters off of South America, redistributing the thermal profile of the Pacific Basin. So this is the surface map over here on the left, and this is the depth map showing the progress of hot water, relatively speaking, and moving it over to the Americas with the ENSO phenomenon. There is a counter phenomenon to this which produces cooling known as La Nina, and it again has an impact on the climate as well. When you're dealing with geologic views of the Earth, you have to realize that the sea levels have not always been where they're currently at. We like to use the modern sea level as a reference point and datum. We actually saw it when we were talking about contour maps. We used our 0 point, our datum point, as average mean sea level today. But in fact, the sea level moves up and down over time and has moved dramatically throughout Earth's past. One of the most dramatic incursions of high sea levels, most recently in geologic time, is about 60 to 90 million years ago during the Cretaceous. So the Cretaceous period would have seen an incursion of seawater throughout the central U.S., covering the entirety of Texas and the interiors of the plain states, all the way to the mountains within the interior of North America and through Canada. This meant that we had shallow, warm, sunlit waters within these regions, and the impact was definitely great on the geologic system. We have lots of examples of organisms that lived and died and proliferated during this time, and they left behind rocks, much of which makes up central Texas. Sea level fluctuations through time are best recorded since the onset of hard skeletal parts with the beginning of the Cambrian. So a curve like this generally tells us the nature of sea level rise and fall over time. 0 is our modern level, if you will. And as we go back in time, starting with the Paleogene or Neogene and Paleogene, or what's labeled as the Tertiary on this diagram, we see some fluctuations up and down. And I would say our sensitivity to these fluctuations is better as we get towards the surface. But in general, we can recognize that the Cretaceous had some of the highest sea levels we've seen in recent geologic history. Going back in time into the Jurassic, the early time of the dinosaurs, we had lower sea levels. And this means that you might not have continental shelves at all, that they're going to be completely free of water. The last previous large sea level time was in the earliest parts of the Paleozoic, periods known as the Silurian, the Ordovician, and the Cambrian. This is when we saw high sea level incursions. If there's a takeaway from this, it's that our planet has enjoyed relatively high sea levels over time, and lower sea levels have not been particularly dramatic, although there have been some examples from glacial periods within Earth's recent history. And again, these are harder to capture with time. One of the big drivers of sea level fluctuation is the abundance of continental ice on the planet, and of course that ties to the global conditions of warming in the climate over time. But these are huge swaths of time we're talking about here. We're not seeing the sensitivity or any of the detailed information from the modern climate. We'll talk about that a little bit later. Clever folks in geology can make maps of what the Earth looked like in the past. Ron Blakey is an excellent example of this. He's a geologist who worked in New Mexico for a number of years and now has his own company that sells these maps to people. Some stunning maps are often used in textbooks like these, which shows you what the Earth looks like in its past. So if we dial back the time machine to 200 million years ago into the early Jurassic, we can see that the continents are all together here. If we go back 90 million years ago, we have much more separation. So this would have been the formation of the Atlantic. And of course, a difference in what's happening in terms of thermal conditions on the planet and sea level conditions. The sea levels mean that the amount of deposition we see, particularly of marine carbonate rocks, are going to be strongly affected. So we can see that in North America, this is recorded by the onset of sea level fluctuations, that during high stands, we had deposition of marine environments that covered the entire continent. And then, of course, we have periods where sea levels are much lower and we don't have a good depositional record of marine materials. These have sequence names. We won't dwell on them, but these can be used to sort of determine where we are in terms of sea level rises and falls. So the oceans are a dynamic environment. They're deep and difficult to understand. Water on the Earth is mostly saline in nature, and that means that the variations in salinity can actually drive rich systems in circulation. We're accumulating the sediments and the salts in the ocean basins over the time. Sunlight is a major driver of oceanic movement and, of course, the life systems that are dependent on sunlight. The neritic zone is a photic zone. Wave energies can be high there, but life proliferates, particularly because this is an opportunity for benthic life that lives on the bottom, to be exposed to sunlight. Ocean islands also are excellent examples of this, because this is areas sometimes in the deepest parts of the ocean where we have mountain ranges that are a consequence of magmatism underneath that can remain over periods of time long after volcanism has ceased on those islands. Subduction zone trenches are some of the deepest areas on the Earth and very dynamic regions where we don't preserve rock records, but metamorphism is in full swing there. Ocean movement is dynamic and three-dimensional. We only really touched on it, but we should take away some respect and awe for the thermal system that is our modern oceans that generate the climates that many high latitudes enjoy, like in Europe, as a consequence of heat distribution in the North Atlantic, and may be subject to change due to changes in global ice cap formation. Going back in geologic time, the oceans have been dynamic because the climate systems on our planet have been dynamic, and that's because our lithospheric system is dynamic. These are bigger swings of time than our modern incursion into warmth, but nonetheless have had important consequences to the geologic record.